All right, we're back. So just wanted to give you a quick idea of not the adaptive boosting, but the gradient boosting, which is the background behind XGBoost and similar. All right, so it's very similar. It starts off like AdaBoost with boosting, okay? And there's sequential learners being boosted up to a stronger learner, okay? But it works a little differently. So what happens is when we construct the first tree, it's going to be, say, just a stump, just the base and a root node. Then we're going to take it and have it go ahead and try to classify things all on its own. It's going to get a set of errors, this first root tree. All right? We're going to train the next tree in the line, in the conga line, with the residuals, with the errors of the first tree. So what the second tree is going to try to do is not to predict the problem. It's trying to predict the errors of the first tree. Okay? We're not predicting the problem with the second classifier. We're predicting the errors of the first classifier. Got it? And we keep on keeping on that way. So let's say we were trying to predict, in this case, the sale price of apartment buildings in different cities. So how many apartments in the building, where is it located, how old is it, what's the price? Let's try to predict price from those other variables. So the first thing we're going to do is we're going to construct a decision. So I should also say that this is a regression example, right? So we're going to do cart style tree regression. So what does cart style regression do? Well, in each node in the tree, if you remember right, so each split, all we do is, if we're going to do regression, we're going to guess the mean value of all the training data that's within the split, right? So if this is x less than a threshold, and this is x greater than equal to the threshold, right? So for all of the x that meet this criteria over on this side, we're going to take the training data that meet that criteria, find their means, and we're going to guess that for every test set sample that comes through here that happens to meet the x less than t criteria. Okay. So when we start with a root node with just the first element of a tree, all we're going to do is we're just going to guess the mean of the entire data set. So the mean of all this is either 0.5875. Okay. Step 2, we're going to build a tree to predict the errors. Not the prices. We're not trying to predict this. That's not what we're after. What we're after is the residuals. Okay? Just like in regression, the residual is what's left over, the difference between the prediction and the truth. Okay? That's what we call a residual. And that's what's going to be in this category. So we guessed 0.5875 for every single element in this table because we were at the root and we're just guessing the mean of everything. So the actual prices minus the mean of everything gives you a set of residuals, and that's what our second classifier is going to predict or try to. Okay? So if we start splitting, now at this point with the next tree, we can split up. We can say age is less than 30 maybe. Greater than 30, then we go this way. Oh, no and yes, right? You're making my life easy. So, the age is bigger than 30, we go this way. If it's under 30, we go that way, right? And we split on the number of rooms, and we get these setups. So these are the mean values of the training data in all of those. Okay, and again, that's the mean residual, this stuff right here. Okay, so step 3 is we're going to combine the two trees. Here's our root. It guesses 0.5875 for everything. Here's our first tree. It breaks problems up into these leaves. And if we're going to go ahead and predict Lansing, we're going to throw Lansing through that process. We're going to get 0.5875. And Lansing goes over here and comes out to 0.4125. And that hops down and over here. And finally, there's some sort of learning rate because this is a gradient method. We're going to incrementally online head towards this solution. All right, as I said, it's a gradient method. What is it that we are gradienting? Well, we're trying to reduce some sort of error, usually average error, quite commonly for a variety of reasons that I can't get into here, but also sometimes mean squared error or anything else. And so this is our loss function, and our loss function is going to be, again, computed on the residuals, right? So whatever the residual is from the last algorithm in the chain, we're trying to predict that. So we're going to fit a tree to the residual values and try to create terminal nodes on it. And then we're going to pick the output y that minimizes the loss function, the mean squared error, the mean average error. And when we've done that, we're going to update our function with the output is going to be, a learning rate alpha times the sum of y sub outputs over all of the thing, right? So this is a summary idea of how it works, right? The first classifier, it's like golf when you're bad. And I say this as somebody who would never play golf ever. And where I grew up, we called it pasture pool. So you're going to take your swing, you're going to get as close as you can to the target. And that's going to put you somewhere on the loss function. Now we can do gradient descent. We're going to try to, on the next time, try to minimize where we are on the loss function. We're going to try to minimize those residuals by predicting them well. And we're going to get closer and closer with a series of approximations of the error until we eventually click in. Okay, I realize that that was not nearly the level of detail that I covered Ada Boost at, but something has to give. So if you want to know a lot more about gradient boosting, you should head here. This is a really lovely, long, detailed, with lots of examples kind of web page, rather like I gave you for gradient descent et al. Way back when. Okay, so this is a good place to teach yourself gradient boosting. Now the implementations on gradient boosting, XGBoost got quite famous in the mid-2010s because basically every Kaggle prize worth millions of dollars was given to somebody who used a form of XGBoost. So it's a pretty good implementation. I've used it a couple of times myself. It gives you all kinds of possibilities that aren't there in the scikit-learn version of gradient boosting. You have all these different losses, and you can do weighted things and caching of data to make things go fast. And it does seem to be quicker than scikit-learn for the things I've used it for. So okay, XGBoost is lovely. More recently, we've seen a lot of noise, I guess, about LightGBM, which is a Microsoft project, and it is supposed to be faster. I've never used it. Most importantly, it supports GPUs, and when people put gradient boosting machines inside neural networks, which is a thing, then they go ahead and use these light GBM implementations because then it goes well with TensorFlow and whatever. So buzzword, 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 a few more buzzwords. But you can use anything you want if you want to play with these things. All right. That's all I had to say about gradient boosting. It is a very powerful technique which is done very well, but it is not a magic bullet, just like none of these techniques are magic bullets. So let's wrap it up by talking about ensembles as a whole, not just the ones we've talked about. So the whole idea of an ensemble is the wisdom of the crowds, right? If you get together a bunch of different things and they are independently bad, and the way in which they make mistakes is totally different from each other, then we can be quite sure that combining them together, we're going to get a better answer than any one of them separately would likely do. So this kind of thinking, the wisdom of the crowds thinking, is been used to justify ensembles, and we've seen how like the boosting stuff drives everything to zero by putting tiny little increment above chance and multiplying it by a number of classifiers in a multiplicative way, right? All right, so Hansen and Salomon showed a long time ago that we can say, how is it that an ensemble can do better than any individual classifier? So it's necessary and sufficient for an ensemble to be more accurate than any of its individual classifiers is if those classifiers are accurate and diverse. So an accurate classifier is simply a way to say it has lower error rate than guessing randomly. All right, so that just means that an accurate classifier is a classifier which has a gamma greater than 0, to use the eta boost notation, right? It's just a tiny bit better than chance. Okay. So, and diverse classifiers, so it has to be both accurate and diverse. A diverse classifier is going to make different errors than its friends, right? So, I didn't have to write this. It came for free. So if if classifiers are accurate and diverse, we know they're going to do better as an ensemble than any individual most of the time. And you can also see that here with, if you remember bagging, we had this, right? The expected error of an individual, right, is supposed to be right along that line. And an ensemble is, by definition, this binomial thing, which is going to push us into a sigmoid on the error rate. And that means that anytime you are better than chance, so you're on this side, less than 50-50, right, you are positively convex below the line there. So you're always going to be below that chord. You're always going to do better than the individual. So those are two separate ways of looking at the same phenomena, right? Convexity, we know that the chord across is always above something on the convex. Or here, that we can prove that we can drive this towards 0 by just getting a tiny bit better than chance and letting exponential upper bound do its job of pushing down as we increase the number of classifiers. Okay, how do we get diverse classifiers, right? Accurate, well, accurate, we got to have something that can be trained, all right? It's got to be a little trainable. It's got to be able to recognize some of the pattern. I'm not going to go into that. But classifier diversity can be achieved by injecting randomness, okay? We can get randomness by subsetting the training examples, for instance, just like a random forest, because a random forest does bagging. And bagging is a resampling, so we subset the training samples. We can also subset the input features, which is also a random forest kind of thing to do, because each node gets built with a different subset of those features. So boosting rather than subsetting them is going to reweight the training samples so that they have different effects on things. And also, many algorithms are not deterministic. They don't get the same answers every time. If you initialize a random number generator for something, that is also a way to generate diversity. So overall, in the end of the day, we know that ensembles often give us this boost of accuracy at the cost of increasing runtime, right? Because you're not just training one thing, you got to train a lot of things for a given setup. However, some of these approaches, at least the bagging-based ones, they can be parallelized at least. We also know that a lot of contests are won with ensemble solutions. Oftentimes, these are very highly customized, by the way. And we know that ensemble methods do suffer from low interpretability. Okay, but there are attempts at making these more interpretable, more transparent algorithms where we can see why it makes decisions. All right, that is it. Thank you so much for sitting through an extra 15 minutes that you didn't have to. I consider you my friend for doing so. All right. Have fun. Talk to you in the next lecture. Bye.